Hello, everyone, and welcome. Today, we are starting one of the most interesting and, honestly, mind-bending chapters in all of physics, Unit 11, The Dual Nature of Radiation and Matter. Now, I know the name sounds a bit complicated, but don't worry. I promise that by the end of our session today, you will understand it very, very clearly. And most importantly, we will make it completely exam-safe for you. Okay, so to get started, let me ask you a question, a little puzzle. Have you ever thought about this? Why is it that weak UV light from the sun can give you a really bad sunburn, but you could sit in front of a super bright, powerful red lamp all day and nothing happens? How can a weak light be more dangerous than a strong one? It just doesn't make sense, right? Well, the answer to this puzzle is not just some simple fact. It's actually a deep secret of nature, a secret that totally confused the greatest scientists about 100 years ago and made them question everything they thought was true about light. You see, for hundreds and hundreds of years, everybody was sure about one thing. Light is a wave, just like a wave in the water. And if you think about an ocean wave, a bigger wave is more powerful, right? It has more energy. So it was simple logic. Brighter light means a bigger wave, which means more energy. Simple. But that simple idea failed completely when scientists did experiments. They studied something called the photoelectric effect, and what they found was shocking. The old wave theory predicted that if you use brighter light, electrons should fly out with more energy. But what really happened? The energy of the electrons had nothing to do with brightness. It only depended on the light's color. The theory said any color should work if it's bright enough. But in reality, a super bright red light did absolutely nothing, zero, while a faint, dim violet light worked instantly. Physics was in big, big trouble. And right in the middle of all this confusion, a young genius named Albert Einstein came along. And he didn't just suggest a small change, no. He came up with a completely new idea, an idea that changed science forever. Einstein's idea was just brilliant. He said, what if light is like a great actor? You know, in some movies, the actor plays a gentle, flowing role. That's light acting as a wave. But in other movies, the same actor plays a tough, hard-hitting role, and that's light acting as a particle. It's the same light, you see, but the situation, the experiment, reveals a different side of its personality. And he gave a name to this particle character of light. He called it a photon. So what is a photon? It's simply a tiny, separate packet of energy, a little bundle of light. So don't think of a beam of light as a continuous river. Think of it more like a machine gun firing millions of tiny energy bullets. And this is the golden formula that explains everything. The energy, E, of one single photon bullet does not depend on how bright the light is. It depends only on its frequency, V. And what is frequency? It's just what our eyes see as color. A high frequency means a color like violet or blue, and a low frequency means a color like red. That H you see is just a fixed number, Planck's constant, so don't worry about it. So this perfectly explains our sunburn puzzle. The sun's UV light has very high frequency photons. Each single UV photon is like one powerful punch. Wham! It hits a skin cell and has enough energy to knock an electron out and cause damage. But the red lamp, it's shooting out millions of low-frequency photons. Each one is like a gentle tap. And it doesn't matter if you get a million gentle taps, it's never going to be the same as one strong punch. And you can just see it in the numbers. A single violet photon has almost double the energy of a single red photon. That difference is everything. The violet photon has enough energy to do the job, to kick out an electron. The red one, well, it just doesn't. At this tiny level, it's an all-or-nothing game. Now, if you think that's strange, hold on, because the story gets even weirder. If light, which we all thought was a wave, can act like a particle, then could it be the other way around? Could a particle, like an electron, sometimes act like a wave? This was the incredible idea of a scientist named Louis de Broglie. He suggested that every single moving thing in the universe, an electron, a proton, a fast bowled cricket ball, even you, has a wavelength. This isn't just a thought experiment. It's a real, measurable property that you can calculate with this formula. And his reasoning was just beautiful. It was about symmetry. He thought, look, Einstein gave particle properties, like momentum, to light waves. Surely nature is fair, right? So he argued matter particles must have a wave property, a wavelength. This wave-particle duality isn't just a weird thing that light does, it's a fundamental rule for everything in the universe.
Okay, chalo, let's talk about some very common mistakes that students make, which can lose you marks in the exam. I call them silent killers. because they seem logical, but they are wrong. Let's make sure you don't fall into these traps.
Okay, first big mistake. So many students think that if you make the light brighter, the electrons will fly out faster. It makes sense, no? More powerful light, faster electrons. But it is completely wrong. Brighter light just means you're shooting more photons per second. So you will get more electrons coming out, yes, but the speed of each electron is decided only by the color, the frequency of the light. So here is a very simple way to remember it for the exam. Just repeat this in your mind. Frequency is the gate. Intensity is the flow. The frequency decides if the gate is even open or not. And once the gate is open, the intensity, or the brightness, decides how many electrons can flow through per second.
The second silent killer is this idea that light switches its form. Like, on Monday it decides to be a wave, and on Tuesday it decides to be a particle. No, that's not correct. The truth is light is always both at the same time. It has both wave and particle properties. It's just that the experiment you choose to do will reveal only one of its faces, like looking at only one side of a coin.
So, let's put it all together now. It's really important to see how this chapter connects with what you've studied before and what you are going to study next. Remember, physics is one single, beautiful story. See, in the earlier chapter on electromagnetic waves, you learned all about how light is a wave, right? This chapter doesn't cancel that. It just adds a new piece to the puzzle. Light also has a particle nature. And looking forward, this idea of the photon, this formula E = h nu, is absolutely essential for the next chapters on atoms and nuclei. You simply cannot understand how an atom works without it. So, for your final revision, here are the main points. 1. Light is made of energy packets called photons. 2. A photon's energy depends only on its frequency, its color, using the formula E = h nu. 3. All matter, everything, also has a wave nature. And 4. This whole idea is called wave-particle duality, and it's a basic rule of the quantum world. And I'll just leave you with one final question to think about. Experiments have proven that a single electron, which we think of as a tiny dot, can behave like a wave and pass through two different slits at the same time. Now, if a fundamental building block of our world can be in two places at once, what does that say about the solid reality that we see and feel every day? Think about